Hi, welcome back. We're in the second segment of Lecture 9 on multiple regression analyses in R. So in the last segment, we ran one multiple regression analysis. And in this segment, what I'd like to do is run it again, but now get standardized regression coefficients and compare the results of multiple models. And we'll do that through model comparison. So the goals for this segment are, again, to write a script. So this is one of the lectures where I'd like you to follow along in R and try and write the script that I'm building as I walk through the lecture. We'll do a multiple regression analysis, again, just like the last segment, but we'll get standardized regression coefficients, and that's real easy. And since that's so easy, I needed to fill up some time for this segment. I thought I'd show you how to compare multiple models. And we can compare the R-squareds of multiple models and do significance tests on those R-squared comparisons. So again, the example we're dealing with is this example that I just made up, where we have an outcome variable y that's physical endurance, two predictors, age, and the number of years that someone has been actively engaged in exercise. And in the last segment, we just ran a multiple regression analysis, but we only got the unstandardized regression coefficients. And this is another aspect of R that's a little bit unique. In most software packages, if you run a regression analysis, the software will automatically give you the unstandardized regression coefficient and the standardized. R, you actually have to go in and ask for it. And that's typical of R. And at first, it might seem annoying, but it's actually, to me, a really great thing, because what it means is you really have to know what you're after to get the output. You can't just point and click and randomly get results and try and interpret them. You have to really know what you're writing into the code, and you have to know how to read that output. So we're going to go in and fix the code to get the standardized coefficients. And it's really simple. All we have to do is put the function scale in front of all our variables. What that does is it standardizes all of our variables, and then we have standardized units and standardized regression coefficients. So R is pretty clever with that. Because that's so easy and it'll happen so fast, I decided to compare some of these models that we're running. And the way to compare models is to use the ANOVA function. And we're going to do ANOVAs later in the course. That's analysis of variance. This is just a function in R that allows us to compare amount of variance explained by multiple models. So here's the additional code to script into the script that we built in the last segment. So I'm not going to walk you through all of that code again. And again, remember, there are a lot of assumptions we should be testing here. So the tests for univariate normal distributions, linear relationships, homoscedasticity, and so on. I'm just showing you what's new. And what's new is doing multiple regression analysis, asking for standardized regression coefficients. So that's in my comment. I'm doing regression analyses, standardized. And the way I do that is just use this scale function and put it in front of every variable. Every y variable, every x variable. And the way I noted that in my code is, remember from the last segment, I just had model 1, model 2, model 3. Now I just put a z on those to signify that these are standardized. So I have model 1.z, model 2.z, model 3.z. And again, they're the same models that we ran last time, just two simple regressions, and then model 3 is the multiple regression with both predictors in there. I can then do model comparisons, so I can see if adding in that both predictors in one model, I can see if that does better than having just one predictor in the model. And I can do that with a formal test. And this works statistically because these are models that we call are nested. So this model is nested within the more complex model. So we can do this direct model comparison. And there's a significance test that allows us to test whether or not this model is doing statistically significantly better than the simple regression models. So I'll compare model 1 to model 3, and I'll compare model 2 to model 3. And here's the output for the first model, where we're just putting age in to predict endurance. And again, what I've done at the top of the slide is I've just put in the regression equation from this output. And I got those estimates again from this little piece of the R output. Now, one thing to notice is, what's the predicted score on Y when the X's are 0? Well, it's 0 because everything's standardized, right? So now the regression constant is 0. The other thing to notice is the regression coefficient for age is the correlation between age and endurance. And I'll show you the correlation matrix in a moment, but we'll look at the correlation analysis and you'll see that that's the correlation coefficient, because if you have just one predictor in the model, then the standardized regression coefficient is the same as the regression coefficient. If you have more than one predictor in the model, that won't hold. But with one, it is. So that's just the correlation between age and endurance, negative 0.13. Not very strong, but as we would imagine, negative. The other thing to notice here in the output is, again, we're only explaining 1.5% of the variance. So the model R squared will not change at all when we go from the unstandardized to the standardized solution. All we've done is we've rescaled all our variables. So the percentage of variance explained is exactly the same. So these t-values, these p-values, the R squared, those things don't change. What will change are the actual regression coefficients. Now let's look at the simple regression with active years in the equation. Again, the regression constant now is 0 because we've standardized, and the regression coefficient for active years is the correlation between active years and endurance. So it was 0.34. And again, the way I got those was I just looked at the estimates in the R output. And again, the model R squared doesn't change from the unstandardized solution to the standardized solution. So the model R squared is the same as in the last segment. We're explaining 11% of the variance in endurance from active years. So it's doing much better than age. But what happens when we put them both in together? This is where we see what I was saying is that interesting pattern is, and it's hopefully it's easier to see now that we're dealing in standardized units. Remember, age before was negative 0.13. Now we're up to negative 0.24. Remember, it's just the absolute value of these things that matters, right? So age is now having a stronger effect when we put in active years. Likewise, active years is having a stronger effect when we put in age. We're up to 0.4 now, whereas before we were at 0.34. We're up to now 0.4. Again, I got those coefficients from the estimates in the R output. And if we look down at the model R squared, we're now up to 16.6% of the variance. So knowing the number of active years that someone has been engaged in physical exercise and their age, knowing that linear combination allows us to explain more variance than if we know each variable in isolation. Because remember, we only explained 11% of the variance from active years and about 1% of the variance from age. So we just added those together, that's 12%. But in this model, by putting them together, we're explaining 16.6% of the variance. That's the beauty of doing multiple regression analysis. What we're doing is we're finding the best linear combination of these predictors to explain the outcome. So knowing both the number of active years and someone's age allows me to explain more than knowing either one in isolation. And again, they got stronger because what these estimates represent, and this is the most important thing to take home from multiple regression analysis, is remember how to interpret these regression coefficients when there are multiple predictors in the equation. The regression coefficient, again, it's always just for a 1 unit increase in x, it's the predicted change in y. But when there are multiple predictors in the equation, then it's the predicted change in y for the average level of every other variable in the equation. So this is now the slope of endurance relating, the slope of active years relating to endurance for someone of an average age in this sample. And likewise, this is the relationship between age and endurance for someone who's of an average amount of active years of exercise. That's the way to interpret the regression coefficients when there are multiple predictors in the model. This last piece that I'm going to do in lecture 9 and in this segment is just compare these models. And as I said, statistically, we refer to these types of models as nested because one just builds upon the other. So we can do a direct statistical comparison of model 1 and model 3 and then of model 2 and model 3. And we do that using the ANOVA function in R, and this is the output from R. And there's a lot in here. I'm just going to focus on a couple things that you've seen before in the lectures. First, I'm going to bring your attention to this RSS column. That's the residual sums of squares. Remember, we talked about that. We were trying to minimize the residual sums of squares. And what you can see is you go from model 1 to model 2. This is actually, in my terminology, 1 to 3, but it just lists 1, 2 in this output. What you see is the residual sums of squares goes down, right? It goes from 240 down to 200. So we're doing a better job at minimizing those prediction errors because we added in another predictor. So the residual sums of squares goes down. And if I compare the overall amount of variance explained in those two models, I can run a significance test. We'll talk more about this later in the semester. But I can run a significance test. It gives me an F ratio that gives me a p-value. And I have a very low p-value, meaning that these two models are statistically different. That is, the more complex model with both predictors in the equation is accounting for significantly more variance than the simple model. And if I do the same thing, comparing the model with active years in it to the more complex model, again, I get a significant result. So the more complex model is doing better, but the difference isn't quite as strong. And that's because active years by itself does a pretty good job. Remember, it explained 11% of the variance just by itself. But adding an age with it gets us up to about 16.6% of the variance. And if we do this significance test here through this model comparison using the ANOVA function, we see that that's a significant change. So going from 11% to 16% in this example is a statistically significant change. We're going to spend some time talking about exactly what that means, statistically significant, and how we get that from a low p-value. But for now, we can just conclude that this more complex model with both predictors in it is doing better than either one of the simple models with each individual predictor working alone. And the last thing I wanted to do is just compare these standardized regression coefficients to the correlation matrix, because this is actually a way to check your work and make sure you're doing everything right. When you do the simple regression equations asking for the standardized coefficients, they should just equal the correlations. So I got this output just by running the core function on my data frame, and there's only 3 variables in there. And endurance is the outcome measure. Here's the correlation with age. We've seen that, negative 0.125 or negative 0.13. And here it is with active years, about 0.34. Let me just go back. There's that 0.34. This is when I put active years in the regression equation by itself, and I used the scale function in R to get the standardized regression coefficient. The standardized regression coefficient, 0.34, is the regression coefficient. So it's just a way of checking your work. So these things match up. When we did it with age, it was negative 0.13. Did it with active years, it was 0.34. Then after my model comparisons, I ran the correlation matrix, and there you see the same values. It's just a way of checking to make sure that we did those standardized regression coefficients correctly. And again, the take-home message from this is that putting these two predictors together explains significantly more variance in the outcome measure endurance than looking at either one alone. And the other thing that this segment allowed us to do is move from unstandardized to standardized regression coefficients. And that's really handy when we're dealing with variables like this endurance variable that have really arbitrary scales. And this segment allowed us to do model comparisons and see if there are significant differences between or among different models. And as we saw, the more complex model does best.